Hello, students. This is Mr. Ezra. Today we are going to talk about binomial expansion. Binomial expansion is one of the coolest things that we talk about. It's a really neat trick that allows us to expand binomials with some ease. The first thing that we need to talk about before we get into binomial expansion is Pascal's triangle. Pascal's triangle is formed by starting at the top of the triangle with the number 1. And then as we go down the outsides of the triangles, we're always going to have 1s. Every row on the outsides, there are going to be the numbers 1s. And the way we get all the numbers inside is the two numbers that are above add together to give us a new number. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. And we would do this all the way down the triangle. And you can see I've already kind of filled in all these numbers. And just by adding, 20 plus 15 is 35. 35. So take all my little shading off. So here is Pascal's triangle. Now, Pascal's triangle is a really neat thing. If you want to waste some time on the internet, just do a Google search for Pascal's triangle. I found a page called mathisfun.com, which has lots of tutoring help, by the way, but also has a lot of neat stuff about Pascal's triangle. One thing that is neat is the diagonals have special patterns. For example, the first row, well, I don't know if you'd call that a row, but the first diagonal is nothing but 1s. The second one are the counting numbers. The third one are called triangular numbers. So these are numbers that, like, 3 is a triangular number because 1 and then another 1 and 2 makes 3. 1, 2, 3, and it makes a triangle. If I add 3 more on, now I have 6 of them, and it makes a triangle. If I add another 4 on, now I have 10 of them, and that makes a triangle. So these are triangular numbers. The fourth row are called tetrahedral numbers. You can look up that. That's a really cool thing. There's tons of patterns in Pascal's triangle. For example, the horizontal sums. So there's a pattern, 1, 2, 4, 8, 16, 32. Do you notice anything about those numbers? They're all powers of 2. Another pattern that is in Pascal's triangles, the number themselves, when you just look at them, are all, each row is an exponent of 11. The first row is 11 to the 0th power is 1. 11 to the first power on the second row is 11. 11 to the second power on the third row is 121, and you can see that that pattern continues all the way down. So there are lots of cool patterns with Pascal's triangle. If you take the odd numbers and the even numbers and you color them different colors, you end up with a cool thing called Sierpinski's triangle. It's a really neat pattern. You could go through this web page and spend quite a bit of time looking up all the cool stuff about Pascal's triangle. Well, today we are specifically going to be looking at something called binomial expansion. And what we want to know, well, there's Sierpinski's triangle, right? What we want to know is how can we use this triangle and the patterns in these triangles in order to expand polynomials. So we'll start with anything to the 0 power. Even a binomial to the 0 power is 1. That is the first row of our triangle. We call it the 0th row because it's the 0 power. Anything to the first power is that thing, so x plus y to the first power is 1x plus 1y. For the second, look at the coefficients here, 1, 2, and 1. Do you notice that they come from this second row here of the triangle? X plus y to the third, what would be the coefficients? 1, 3, 3, and 1. You suspected that, you'd be right. And we'll go to the fourth power. Well, before we go to the fourth power, let's talk about the x's and the y's. I want you to notice a pattern, especially here with x plus y to the third power. X is raised to the third power on the left, and then we do a countdown to the second power, to the first power, and then you'll notice there's no x in the last term. The second term in our binomial, y, is raised to the third power on the right, and then the second power, the first one from to the left of the right, and then the next one is just y to the first, and then there's no y in the front. And we'll see that pattern as we work through these, that your first term is going to start with the exponent and then work its way down, 3, 2, 1, 0, and then the second term is going to start at the end and work its way down. So x to the fourth, our coefficients are going to be 1, 4, 6, 4, 1. This is the fourth row. And you got to kind of get used to this. This is a little different, but the top row of the triangle is called the 0 row. And then we have the first row, second row, third row. We need the fourth row, which is 1, 4, 6, 4, 1. These are going to be the coefficients in our expansion. Our x's are going to start at the fourth power because this is raised to the fourth power. So we'll have x to the fourth, then x cubed, then x squared, then x, and then x to the 0, which is 1, which is why we won't see an x in the last term. We then go the other way with our second term. Our y's are going to count down from the right. So we got y to the fourth, y to the third, y squared, y to the first, and then y to the 0, which is 1. So this right here is 1, and this x to the 0 is 1. So they kind of really don't even count. You won't see a y in the first term, and you won't see an x in the last term. And when we clean that up, we end up with 1 x to the fourth plus 4 x to the third y plus 6 x squared y squared plus 4x y to the third plus y to the fourth, 1y to the fourth. And those ones are unnecessary, but I want you to see that where the ones come from. They're the coefficients from the triangle. This might seem a little weird at first, but I promise you it's a lot faster and less painful than multiplying x plus y times x plus y times x plus y times x plus y once you get used to the pattern. So let's look at some examples. All right, so let's use the binomial theorem in Pascal's triangle to write each binomial expansion. So this is example 5 if you have your packet out. So remember when we do Pascal's triangle, the first row is always 1, and that's really called the 0th row. And then the first row is 2 1s. And then for the third row, we've got 1, 2, and 1 because 1 plus 1 is 2. And this is our second row. This is the one we want because we're raising this to the second power. So we're going to start with 1, 2, and 1. 1, 2, and 1. The x is going to be raised to the second power, then to the first power, then to no power, which is just it's not gonna be there. The 3 is gonna start at the right, and it's gonna be raised to the second power. What is 3 squared? 9. And then 3 to the first power is just 3. And then you won't have it, a 3 to the 0 power is 1, so there won't be anything there. And we just add these things together to get x squared plus 6x plus 9 once we clean up. And this is x plus 3 squared using binomial expansion. Now, I'm going to clean up the ink here. So we can see that the 2 means that we need to go to the second row of Pascal's triangle. It's going to be the coefficients 1, 2, and 1. The x squared is going to fill in descending order. The 3 squared, 3, and then 3 to the 0 in kind of starting up with on the right side. And then when we clean up, we get x squared plus 6x plus 9. When we want x minus 2 to the fourth power, that means we need to go to the fourth row of Pascal's triangle. Now, if you don't have Pascal's triangle handy, you might want to kind of keep that with you when you're doing these. And on like a quiz or a test, if you don't have it handy, you just draw it really quickly. Just on your test, you go 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so forth. Well, we want to go all the way down to the 1, 4, 6, 4, 1 row because this is to the fourth power. 0, 1, 2, 3, 4. This is the row that we want. As we're filling these things in, those are the coefficients that we're going to use. We're going to start with x to the fourth power on the far left, and then x to the third, and then x squared, and then x. The last term will not get an x. It's really x to the 0 power, but that's just 1. On the right side, we're going to start with negative 2. Notice it's not just 2, but negative 2 to the fourth power, which is going to end up being a positive. Negative 2 to the third power in a minute is going to end up being a negative. So the negative is important. We got to keep it in there. Negative 2 squared, then negative 2, and then the first term is not going to get a negative. So it's get your coefficients. Then descend with exponents on your first term from the left, descend with the exponents of your second term from the right, and then clean up. And when we clean this up, we need to make sure that we raise everything to the power that it needs to be raised to. And then we're going to multiply any numbers that are part of a term that haven't yet been multiplied. So 4 times -2 is -8, so we put -8. But 6 times +4 is +24, so we put +24. And the exponents and the variables come down. Oops. And that is the answer. You want to try one? Pause the video, give this one a try, and then start the video up and we'll look at it. X plus 5 to the 4th power. Well, you might have noticed when you're doing this, if you pause the video and tried it, that you got some larger numbers. And the reason is when you start raising 5 to the 4th power, 3rd power, you get much larger numbers than if you're raising 2 to the 4th power. Remember that the 4th row is 1, 4, 6, 4, 1 in the triangle. That's where we get our coefficients from. You should have counted down with your x's, x to the 4th, x to the 3rd, x squared, x. You should have counted down from the right with your 5 to the 4th, 5 to the 3rd, 5 squared, and 5. And then as you clean this up, you would have dealt with raising all of those exponents, all those 5s to their exponent. And then, so like 5 squared is 25, but then 25 times 6 is 150. 5 to the 3rd power is 125, and 125 times 4 is 500. So the cleanup is going to look like this. It's going to be in descending order. It's going to look awesome. So hope this is kind of making sense to you. It's one of those things that once you get it, it's super easy to use. You just kind of have to practice it. Let's look at example 8. It's a little bit different. We're still using Pascal's triangle to get our coefficients. So our coefficients are going to come from the 3rd row of Pascal's triangle, which is 1, 3, 3, 1. But when we expand out 2x to the 3rd power, and then 2x to the 2nd power, and then 2x, we've got to raise both the 2 and the x to that power. And of course, 1 is going to be 1 to the 3rd, 1 squared, 1, and then the first term doesn't get a 1. And those are going to be easy to deal with because 1 to any power is 1, but 2x to the 3rd power is 2 to the 3rd power and x to the 3rd power, giving us 8x to the 3rd power. So I'm just throwing this in there just in case you get one like this, that whatever this first term is, you're going to raise it to powers descending from the left. Whatever the last term is, you're going to raise it to powers descending from the right. And if you do that, these questions should be pretty easy for you to clean up and get the right answer. In this case, it's 8x to the 3rd power plus 12x squared plus 6x plus 1. Well, I really like Pascal's triangle. I really like binomial expansion. I think if you practice it and ask questions when you got them, you'll find that it's way easier than multiplying 2. Please let me know if you have any questions, and I will see you in class.